Okay, so this lesson on 7.4 is evaluating and graphing logarithmic functions. Our goals are to change exponential expressions to logarithmic form, change logarithmic expressions to exponential form, and we want to evaluate and graph logarithmic expressions and functions. The logarithm is, strictly speaking, the inverse of our exponential functions. And this used to be used a long time ago, especially when we were trying to add or multiply really large numbers. And there's a property of logarithms that allows us to do that much more simply. It also lets us find the exponent when we're not sure what the exponent is. And so we can kind of create the graph of the logarithm and use that graph to our advantage. And we're going to learn what that graph looks like, and it's all based around our exponential functions. So we got to keep that in mind while we're doing that. Okay, so we have our key concept here. Let b and y be positive numbers, with b not equaling to 1. The logarithm of y with base b is written as this: log of y base b. Or I like to say log base b of y equals x. Alright? And then what we're going to do is we're going to translate that to exponential form here. So we have b to the x equals y. So what this x right here is telling us is this x is our exponent in exponential form. This y is our value in exponential form, and this b is our base in exponential form. So it might help to write it right underneath. We have log base b of y equals x. So this x went there, this y went here, and our base went there. Okay? So I want to write our log in exponential form. So for a here, we have log base 2 of 32 equals 5. So what that says is 2 to the 5 equals 32. Alright? So for b here, we have log base 5 of 1 equals 0, or 5 to the 0 equals 1. Alright? And then for c we get log base 10 of 10 equals 1. So we have 10 to the first equals 10. D, we have log base 10 of 0.1 equals negative 1. So we write that as 10 to the negative 1 equals 0.10. And then our last one here is log base 1/2 equals negative, of 2 equals negative 1. So that says that 1/2 to the negative 1 equals 2. Which we know because a negative exponent flips whatever fraction you're working with. Alright. So here we have a couple special logarithms that we saw in the last one. Anytime you have a 1, logarithm of 1, so log base, any base of 1, you always get 0. Because anything to the 0 equals 1. So you could have log base 1,000 of 1, you will get 0. Alright, here we have log base b of b, so when the base and the value match, it always equals 1, because that means b to the 1 equals b, which is the case we know, because anytime the exponent's 1, it just equals whatever your base is. Alright, so log base b of b equals 1, always. So you could have any base there. Log base 10 of 10, which we saw in the previous example. Log base 20 of 20. Log base 1/2 of 1/2. Anything. Alright? Alright, so now we want to evaluate the expression. So when you're evaluating logarithmic expressions here, all you're really doing is saying, what is the exponent? My answer will be an exponent. Alright? So we're saying here 3 to the what? Oh, that was a terrible question mark, by the way. So 3 to the what equals 81. Well, then you got to figure that out. But 3 to the 4th equals 81. So my answer is 4. Here we're saying 5 to the what equals 0.04. Well, you might not be super familiar with this, but we know that 1 over 5 is equal to 0.2, and 1 over 25 is equal to 0.04. Well, 1 over 25 is 5 to the negative 2. So our answer here is negative 2. All right. Log base a half equals 8, so 1/2 to the what equals 8. Well, I know that 2 cubed is 8, so how do I make a negative, or a half, 1/2 turn into 2? I use a negative exponent. Okay, so if I use 1/2 to the negative 3, that would change my answer to 8. All right. And then we have 9 to the what equals 3. Well, 3 is the square root of 9, so our exponent for square roots is 1/2. Whereas 9 to the 1/2 would equal 3. Okay, here we have our, just doing some stuff with calculators. So our expression is log of 5. And notice there is no base for a here. Anytime there's no base, we assume base 10. Why base 10? Well, hold your hands out. Look at your fingers, wiggle them. How many of those are there? Yep, there's 10. So that's why we assume if there's no base written, we always go with base 10, which is what your calculator does. So your log button on your calculator, which should be right next to 7, to the left of 7, is base 10. So I hit log 5, enter, and I get about 0.69889. Alright, there's our answer. Then we have ln. ln is a good little intro into ln. ln is the same as log with a base e, our natural number that we learned in section 7.3. So we have a natural log is what this is called, short version of this. Okay, we use it so often in calculus and things that we created a shortened version of it. So right below log button is ln of 0.1 and enter. So then we end up with negative 2.303. And I rounded a little bit at the end there, in case yours doesn't look exactly like that. Okay, here we have a science little experiment. And, okay, so what they tell us is that the slope S of a beach is related to the average diameter D in millimeters of sand particles on the beach given by this equation. Okay, so someone took the time to measure slope based on the diameter of sand or sand particles at the beach. We want to find the slope of the beach if the average diameter of the sand particles is 0.25 millimeters. So diameter is D here, slope is S. Alright, so I'm going to come back up here and we're going to set this guy up. So we're trying to find S. We're given that D equals 0.25. Alright, and so we just plug and chug here. Equals 0.159 plus 0.118 log, so this is going to be multiplication in between the 0.118 and log. 0.118 is the coefficient for log of 0.25. So ask yourself, what base are they working in here? So self, what base is that? They're not writing any base. What base you got? That's right, 10. 10 fingers, 10 toes, base 10. Alright, so that's going to be roughly 0.159 plus 0.118 times negative 0.602, and we use the calculator here. We enter this guy in our calculator, and this is what we got. Alright? Then we simplify, and we get roughly 0.09. So the slope of the beach is 0.09. That's a really gentle slope, and it tells me that for every 100 meters that I go, I only rise 9. 100, 9. And actually, I'm not sure if it's changed, but the slope of a normal ramp that you're allowed to build is 1 to 12, if I remember correctly. So this is really, really slow, really shallow, or not steep, flat, if you will. Okay. Okay, inverse properties. So anytime you have a logarithm here, in the exponent and the base is the same as the base of the logarithm, so we have base 10 log of 2. Remember, log of 2 has a base 10, so anytime the bases match like that, your answer is just 2. Because what the logarithm is an exponent, right? And so we're raising a number to a logarithm, and the argument is your exponent. And so the log and the 10 go away. Right? So, reiterate. Base 10 matches the base in the logarithm, and the logarithm's in the exponent of base 10, then whatever your argument is, whatever your value is, that's your answer. Okay. When you have something like this here, log base 3 of 9 to the x, what you need to see is that 9 is really 3 squared. So 9 is 3 squared to the x, and you have log base 3 of 3 squared, or log base 3 of 3 to the 2x. So anytime your base matches, we can eliminate all of this, and you end up with just 2x. So again, if our value here, the 3, matches our base in the logarithm, then whatever the exponent is your answer. Okay? Okay, we want to find the inverse of a function. This is going to help us graph our function in the future. So again, our method doesn't change. Swap x for y. We have log base 3 of y now equals x. Now we need to solve for y. So the only way to do that now is to write this in exponential form. This is saying 3 to the x equals y, which would be our inverse. Okay? Over here you have the natural log of x plus 1 equals y. So again, we want to say x equals the natural log of y plus 1. And then we need to say, okay, well, this is saying log base e of y plus 1 equals x. So really what you have is e to the x equals y plus 1. And then we subtract 1 over, and you end up with y equals e to the x minus 1. Now you have an exponential function with base e. You've got a k value here of -1, no h value. So if this was a graph, we'd have an exponential growth function, and it would be shifted up, or shifted down 1. Okay, so now we're going to graph logarithmic functions. There is a way where you could plug in values and get certain values out and try to plug it in. But what I want you to do is I want you to notice that this function is the inverse of our exponential function. So if we can find the exponential graph, we can then draw the mirror image and get our graph we were looking for. So that's what we're going to do. So first things first, we need to turn this into our inverse function. So x equals log base a third y and then minus 1. So first thing I'm going to add, so right now there's no parentheses here. If there were parentheses there, then I would have to keep that as part of it, but it's not. So I just say I add the 1 over because I want to get my logarithm by itself. Add 1. So I have x plus 1 equals log 1/3 y. So then what I have is I have an exponent here. I have 1/3 to the x plus 1 equals y. And if you're saying, well, that's a decay function, you are correct. Okay? And so what we have here is we have a decay function with a base of third and an exponent of x plus 1. So our h value here is -1. So that means we're moving to the left 1 unit. I need to create my xy chart to find my new points. And our OG would be 1/3 to the x, and then y. So we're going to get 0, 1. 1/3 to the 0 will equal 1. 1/3 to the 1 will equal 1/3. Okay. So now when I go to graph this, alright, I'm going to go out to 0 and up to 1. And then I'm going to go out to 1 and up to 1/3. So this is exactly the same as our exponential function. So it's going to have an asymptote here of y equals 0. And then we're going to, let's erase that. That looked a little ugly, sorry. So then we swoop down. And we have our original graph, our OG. Okay. Now we need to just shift it. The only shift I see is that it needs to move horizontally in the negative direction. So I'm going to move each point 1 unit. So this guy is coming over here. This guy is coming over here. And I'm going to do that in blue. So our new point sits right there. And our new point sits right there. There is no, what do you say, there is no vertical shift, and so I don't need to move up or down. So my asymptote doesn't have to change. So I can fill this in with blue and say that my asymptote is y equals 0. To get my domain would be all real so far, and my range would be greater than 0. But so far all we've drawn is our inverse. We haven't drawn the actual logarithmic function yet. So what I'm going to do is in red here, I'm going to put the mirror line. All inverse functions, all of them, mirror each other. So the original f of x mirrors across y equals x from f inverse of x. So if the blue line is our inverse, we just swap the x and the y values for our points, and we get the new x and y values for our final graph. So let's pick a different color. Let's go with green. Okay. All right. So this point here is -1, 1. So my inverse, or excuse me, our original graph, since we've drawn the inverse, is going to be 1, -1. So it has a point right there. And I'm going to erase this equation for our asymptote to get it out the way. Clear up some room. And then our other point was at 0, comma, 1/3. So in blue here, that's this point, 0, comma, 1/3. And so what I want to do is say, well, I've got another point then at 1/3, comma, 0. Which is going to be right about there. And then what we have to notice now is that our asymptote will shift from being a y equals to an x equals asymptote. It swaps. It becomes a vertical asymptote. And then I draw my graph to look mirrored. Here and there. So now what we have is we have a domain of x greater than 0 and a range of all real, which is the exact opposite of what we used to have back last section with the exponentials. We had domains of all real and ranges of either y greater than 0 or y less than 0, or depending on what the asymptote was. Oh, speaking of asymptote, our asymptote is now x equals 0, the equation of a vertical line, as opposed to y equals 0, the equation of a horizontal line. Okay, so general strategy on this bad boy is to graph the exponential. Then we graph our mirror line. And again, our mirror line is right here. It's this red line. Okay? That's what we're mirroring across. If you'd set a mirror across that line, the blue line would turn into the green line. And that's what we want. We graph the blue line, and then we mirror it to get our green line, which is our final graph. Green is final. Okay? So let's try the next guy. Let's see, eraser. Can I erase? No. Apparently I can't erase. Alright, I'll try. Continuing our graphing, we're going to do b here. And b is log base 5 of x plus 2. Alright, so this is a little different because now the x plus 2 is in parentheses. So what we need to do is, again, we need to say, alright, x equals, maybe we could thin that out a little bit. There we go. Erasure. So x equals log base 5 of y plus 2. So we have what this, if I turn this now into exponential form, I say 5 to the x equals y plus 2. So then I have 5 to the x minus 2 equals y. So now what I'm going to have is a vertical shift down, because k equals negative 2, but h equals 0. So there's no horizontal shift. Okay? Alright, so we're going to graph our exponential. This is what we call our f inverse. Right? So this is our inverse of our original f of x up here. And we're going to graph him first, then mirror him to get back to our original function. So we'll put the graph over here, and then we'll put my xy chart here. X, y, and we get our OG is 5 to the x, and we'll say what's 0 and then 1. So 5 to the 0 is 1, 5 to the 1 is 5. So our OG graph of our exponential without shifts starts at 0, 1. Oh, you know what? Maybe I'll make that a little lower. So let's fill this in. And then we'll go right here, buckle up our sleeves, and away we go. So 0, 1. Okay, and then 1, 4, 5. And then our starting asymptote is down here at y equals 0, which will shift now. Okay, so our graph looks like this guy. Okay, our mirror line is at y equals x. It's this dashed line that I'm drawing. It's diagonal. Y equals x. And then we need to, you know what, before we draw that, why don't we why don't we go ahead and shift this thing first. Sorry, forgot to shift it. We need to shift down 2. So we're going to go down 1, 2, and every point is just going to shift down 2. So we'll do that line in, we'll do that line in red. So down 2, and down 2. And our asymptote shifts down 2 as well. So y equals -2 is our asymptote. Then I can go ahead and draw my new line. Alright, so there's our inverse. Cool. I still draw y equals x, like normal. And then I'm going to do the inverse of that. So everything changes, right? Everything swaps. So our new asymptote is at x equals -2. Okay? We had 0, -1 for 1 point, so I'm going to have -1, 0 here. Then I had 1, 3 for this point, so it's going to be 3, 1 now. So 1, 2, 3, 1. And it should come from here and curve on down. Total mirror images of what we had before. Alright. So we have our black graph that represents the original exponential function, where we have 5 to the x. Then we shift that according to our k, which is -2, and that becomes the red guy. Then we take our final exponential guy, which is our inverse function at the moment, and we're going to flip it according to y equals x, or excuse me, flip it across y equals x, which becomes our logarithmic function here. So your green function is y equals log base 5 of x plus 2. Okay. So that leads me to some properties. Our graphs of logarithmic functions, summarizing it up here. We have h and k involved. Honestly, for me and for you guys, I'd rather you focus on learning to turn it into the inverse and turn it into an exponential function and then graphing it based on that. Okay? You do need to realize that your vertical asymptote here, x equals h, okay, we're no longer y equals. We have vertical asymptotes for logarithmic functions. Our domain will be x greater than whatever our vertical asymptote is, and the range will be all real numbers, which was the exact opposite of our exponential functions. Okay? And yeah, so that's kind of some of our characteristics of logarithmic functions. But remember, find the inverse, which is an exponential function. Graph that first. Then we can flip it according to y equals x and go from there. Okay? Alright, here's some practice problems for you guys to take a look at. We're going to rewrite exponentials here. Okay, so again, these are example problems. We want to rewrite the equation in exponential form here. So this should be in exponentials. And then here, this should be a value, just some number. If I'm doing 12 here, this is 10 to the log base 10 of 4. Base 10 because it doesn't give us a base. And so we just drop all of that and it just becomes 4. Alright, just for an example. And yeah, if you have any questions, let me know. Thanks.